Hello, all. Welcome to the lecture for Chapter 6 for our Chem 131 class at SMCC. Let's go ahead and begin. You should all have your notes template or some paper to take notes on. Remember that chemistry is the science of doing. So even though you're watching these videos, you need to take notes on them as though you were sitting in class. I am having, so there we go. Okay. Having a lot of technical issues. So hopefully everything will be okay. All right. So first of all, let's go ahead and look at the wave nature of light. So we're going to be learning about some different things. This doesn't get a lot into it, but we talk about a wave particle, a wave nature of light, and a particulate nature of light a little later as well. Okay, so for beginning, our wave nature of light is going to look at some different things. First of all, we have a wavelength, and the character for wavelength is this lambda, like this. That's the Greek character lambda, like so. That should be a, everybody knows I don't spell super well. All right, lambda. And that's the wavelength from here to here. So you can kind of see this is showing you where that wavelength is. Okay, so the next thing that we have is we have amplitude. And we're not really going to be doing a lot with that, but this is our amplitude. It's this height that you can see, all right, off to the side. And then we have frequency right here. And frequency is the Greek character nu, N-U. Okay, and it's expressed in hertz or cycles per second. Our hertz is the same as what we call an inverse second, or maybe a second -1. It just looks a little bit odd. Okay, and then the last thing that we're going to have in there is that the speed of light in a vacuum, or C, is 2.9979 times 10 to the 8th meters per second. And we're going to actually be using that speed for all of our electromagnetic radiation, not just the visible light spectrum that you think about. All right, so let's take a look at, this is where we talk about the wave nature of light, okay? And so when we're looking at this, our speed of light is going to be equal to this C lambda V, okay? So one thing that might be useful is just to remember that we can also solve for our wavelength lambda as C over nu, okay? Because we always know C. So it's not like we're going to be looking for C very often. So either we're looking for a wavelength and lambda is C over nu, or we're going to be looking for frequency, which is C over lambda. Okay. And in this, remember that your lambda has to be in meters. So that's one of the big things that we're going to be working with. And then as a little review there, remember that there are 1 times 10 to the 9th nanometers in 1 meter. And we're going to use that a lot because a lot of light, especially visible light, is always referred to in terms of nanometers. Okay, so now we have our first problem down here, and it tells us that we have a wavelength of 4.47 nanometers, and they're asking us for our frequency. So we're looking for nu. Okay, so this is just a simple, we're going to be using this equation over here, that nu is equal to C over lambda. Okay, and the first thing that we're going to need to do is we're going to need to convert this. So just remembering here, we have 4.47 nanometers. Okay, and working that conversion gives us 1 times 10 to the 9th nanometers per meter. Okay. And I'll go ahead and write the answer over here. And that will give us 4.47 times 10 to the -9th meters. And on the top is our 2.9979 times 10 to the 8th. And that's meters per second. Okay. Now, what I want you to do, I've already kind of worked through this math so that the video isn't super, super long. But what I want you to do every time I do this is I want you to pause, and I want you to practice doing this on your calculator. One of the things that I found is that students often don't put their scientific notation in correctly. And especially when it's in the denominator, if you're typing in times 10, caret, a lot of times you'll end up getting the wrong answer. So you need to make sure that you're getting the same values on your calculator that I'm getting on the screen. Okay. And when we calculate this, we are going to get an answer of 6.71 times 10 to the 16th inverse seconds, and that's the same as hertz. Okay. And that's kind of our final right there. And okay. And that's the frequency of our X-ray light. All right, we are up to our wave, continuing our wave nature of light here, and we're going to be looking at the electromagnetic radiation spectrum. Okay, so right here you can see it showing where we're at in here, and you notice that the units right here are hertz, and this is new. This is our frequency along the top. Frequency on the top, okay, and we have our wavelength on the bottom. And that's our lambda right here in meters. And you can see right in the center here, you have this little rainbow, and that is where the visible light spectrum, the light that we humans can see, is. So the entire electromagnetic radiation spectrum is this really big long thing. And right here, this is where our light is, okay? And the visible light spectrum goes from 400 nanometers in our violets up to 700 nanometers in our reds. And on the other side of things, on this side, we have infrared, and on this side, we have UV. Okay, so for all of this, we're always going to be using that C is equal to lambda nu that we learned on the previous slide. And we're always going to be using the speed of light in a vacuum for all of these. So we can always compare that lambda and nu in there. Okay, that was our wave light properties of light. Now what we're going to do is we're going to be looking at our particulate nature of light. So we could go into all the really fun theory behind this, and this is our Einstein and all that cool stuff in there. But right now we're just going to look at a few things just on the surface for this chapter. But know that if this really interests you, if this is just the basics of quantum mechanics, and it is super, super interesting. So if you take more chemistry, you might be able to learn more quantum mechanics or more physics. It also does quantum. So it's just a really, really fascinating topic. Okay, so in here, we say that our particle of light, or our photon, has an energy value that is associated with its frequency. Okay, so you'll notice here that you have two equations here. Basically, you have E is equal to H nu, and you're going to use that one if you're given a value for frequency. Okay, and then you also have this E is equal to HC over lambda, and you're going to use this equation if you have a value for wavelength. Okay, and the H value in there is just a constant, kind of like R was in the last chapter, and it's called Planck's constant H, and it's 6.626 times 10 to the negative 34th joule seconds. Okay, so our energy is in joules and our frequency is in inverse seconds, which is how this is going to end up working out. All right, so let's go ahead and practice a problem here. And so it tells us that chromium can be detected in atomic absorption spectroscopy by monitoring the absorbance of UV light at a wavelength of 357.8 nanometers. Okay, so that's going to be a lambda. Excuse me. And they are asking for the frequency of our light and the energy of a single photon. Okay, so we'll go ahead and do this in a couple pieces. The first thing I'm going to do is I'm going to go ahead and convert this wavelength. Okay, so, and I'm going to go ahead and do that part up here. And so we have 357.8 nanometers. And we multiply that by 1 meter over 1 times 10 to the 9th nanometers. You'll do this a lot and you'll probably get pretty good at working through it. Okay. And at that point, all right, so this will give us a new wavelength that we can actually use in our calculations of 3.578 times 10 to the negative 7 meters. So you always need it to be in meters to do the calculation. Sometimes you'll have to convert it back to nanometers for your homework or a test question. All right, so once we have that, let's go ahead and find frequency, okay? And you remember that in our equations, we have that frequency is equal to C over lambda, which is 2.9979 times 10 to the 8th meters per second, divided by our lambda value, which we found up here of 3.578 times 10 to the negative 7 meters. Okay. And again, practice your calculations, but that will end up being 8.379 times 10 to the 14th. And the units for that are inverse seconds, which are usually reported as hertz. Okay. And the second part of this problem, these problems often have two parts, so always look for them in your homework and the test, is to find our energy. And energy is equal to, we could use the lambda value, but we just found nu. So we could say, okay, energy is equal to h nu. Okay. And that is going to be equal to our Planck's constant, 6.626 times 10 to the negative 34 joule seconds, okay, times our frequency value here, 8.379 times 10 to the 14, and we're in inverse seconds so that they'll cancel. And what we end up getting for that value is 5.552 times 10 to the negative 19 joules. Okay, so remember, every time I put up an equal sign, go ahead and pause it and make sure that you are getting the same value. So hopefully this math so far is pretty straightforward. All right, going on. Let's talk about quantum numbers. So quantum numbers are basically like an address for every single electron in an atom. Okay, so we have these different ways of describing where you can find electrons in the atom, or rather where you're most likely to find them in an atom. Okay, so first of all, our first one that we have here is the principal quantum number n. Okay, and n is the size and energy of the orbital. So it's the energy level or the size of the orbital. And n can be integers from 1, 2, 3, 4, etc. Okay. Next, we have our angular momentum quantum number, and that is kind of like a cursive L, kind of like that. Okay, it looks kind of like a funny looking E or something. So you'll know what you're seeing. And the angular momentum quantum number describes the shape of atomic orbitals. And this shape is sometimes called a subshell. And L can be any integer from 0 to n minus 1. And so let me sort of show you what that means. So for example, if n is equal to 2, then you have two L values. You have an L value of 0 and 1. Okay, so you start with 0 and you go until you're 1 less than that 2 value. All right. And you'll see that when L is 0, it has the letter S for a designation. When L is 1, you have a P for that designation. When L is 2, it's a D. And when L is 3, you have an F. And from there, it goes G, H, I, J. We just tend not to talk about them, mainly because it only goes through F on the periodic table. So they would just be considered working through with just the letters from the alphabet after that. All right. The third quantum number that we have here is M with a subscript of L. So a lot of times people call that M sub L. So what they're saying when you hear that is M sub L, or M with the subscript of L. And that's your magnetic quantum number. And that talks about the orientation of your orbital in space. So like along the x-axis or along the y-axis or along the z-axis, because our elements are three-dimensional. And M sub L can be any integer from negative L to positive L. So for example, let's say that we have n equal to 3, and then we have L values of 0, 1, and 2. And that means that when L is 0, our M sub L value is going to be 0. When L is 1, our M sub value is negative 1, 0, and 1. When L is 2, our M sub L values are negative 2, negative 1, 0, 1, and 2. And you could keep going with this, and 4, and 5, and 6. And you'll see that there's just these different possibilities of what they are. And in a little while, I'm going to show you what that means in terms of their spatial orientations. Okay. Okay. The fourth quantum number is comes from the Pauli exclusion principle, and it is our electron spin number. We say it can be either plus 1/2 or minus 1/2, and that's for every M sub L value. Okay, so what do we mean for that? Remember that you had the possibility of having M sub L equal to negative 1, 0, and 1 when L was equal to 1. That means that for this M sub L value, you have M sub S as plus 1/2 and minus 1/2. And for M sub L 0, you have an M sub S value of plus 1/2 and minus 1/2. And for L is equal to 1, you have plus 1/2 and minus 1/2. Okay. And what these are is that means half of the electrons are positive, half of the electrons are negative. And a lot of times what we do is we say, okay, every M sub L value, this is an orbital, and these are the 2 electrons in that orbital. And you'll see this in a minute. They have spin up and spin down. Okay, right here. So spin up, spin down, and that's every orbital. Okay, so M sub L negative 1, that's our orbital. Okay, and these values here are the electrons in that orbital. Now you notice here, I've kind of talked over this, but we talk about the Pauli exclusion principle. In a given atom, no 2 electrons can have the same set of 4 quantum numbers. And what that really means is that no 2 objects can be in the same space at the same time. Okay, and the 4 quantum numbers describe precisely where we're likely to find each electron so that there's no overlap. All right, so you can see here we are on slide 9, and slide 9, I have a note here that says, hey, tell you guys to fill in your chart. And I don't know if you can see it up here, but you can see that I have filled in my chart here for 9. Okay, and you want to go ahead and put these in, but let's add a couple of pieces of information to that as we go. All right, so what do we mean here? Remember that this right here is our energy level. Okay, so we have energy level 1, 2, 3, and 4. Now, when n is 1, L can only be 0. And remember that 0 is equal to S. So that makes this the 1s orbital. Okay, or rather that makes this the 1s orbital. Now and in that 1s orbital, okay, we have one orbital, which means that we can have 2 electrons, and they go in, remember, as so there's our number of orbitals. What I want you to add over here on the side, it says spin, and this is just a place to kind of identify where things are at. These 2 electrons would be up and down. Okay, now let's go ahead and take a look at our next one. Now we have energy level 2. Okay, and when n is 2, we can have L values of 0 and 1, and this would be the 2s orbital and the 2p orbitals. Okay, there's 1 2s orbital, 3 2p orbitals. That means that we have 2 electrons and 6 electrons, and these would go in up and down, and we've got 6, so it would be 1 2 3 4 5 6. Okay, and so what that means though is that here you have 4 orbitals in energy level 2, and you can have up to 8 electrons in energy level 2. Okay, and now here we are in energy level 3. Okay, and so this is your 3s orbitals, 3p, and 3d orbitals. Okay, and you can see then your m sub L 0, -1 to 1, -2 to 2, following our pattern. And here we have 9 possible orbitals. Okay, and in them we could have 2 electrons and 6 electrons. I'm just multiplying these by 2, and 10 electrons, which means that in energy level 3 we have a possibility of having 18 electrons. And last but not least, we have energy level 4 here. On the periodic table, we go through energy level 7 on the periodic table. Okay, so you could keep going with all of these, and you just build on them. But in energy level 4, here we have our 4s, 4p, 4d, and 4f orbitals. Okay, and you notice that with all of our orbitals here, we've got 4 orbitals, 9 orbitals. Okay, here we have 4 and 12. We have 16 orbitals. Okay, and that means that we have 32 electrons. Okay, and we would have 2 electrons in our 4s orbitals and 6 electrons in 4p, and 10 electrons in 4d, and 14 electrons possible in 4f. And that's kind of how you're going to be filling all this in your slide 9 on your notes template. All right, now let's take a look at what these orbitals look like. Okay, so and here we only go through a little bit. You have what is called a 3-dimensional coordinate plane here, x, y, and z, and you can see that your s orbitals right here are spherical, and that's definitely a great way. That's the easiest one to draw. All right, now notice that as we work our way up, now we have our p orbitals right here. So here's our s orbitals, here's our p orbitals, and it's almost like this one is doubled. I always think a little bit biology. It's like, oh, look, they're doubling. Okay, so p orbitals have 2 lobes separated by a nodal plane. Okay, and remember that there were p orbitals were when L is equal to 1. And that means that m sub L was equal to -1, 0, and 1. So that means that we have 3 p orbitals available. And these reference their different orientations in space. Okay, so I'm going to draw 3 coordinate planes here. And you could say here's 1 p orbital, and then here's another p orbital, and you can see that what I'm doing here is I'm drawing them along each axis, and we say px, py, and pz. And that's why the M sub L value talks about our orientation in space. All right, last here we have our d orbitals here, and they get harder and harder to draw, but you could draw 5 different d orbitals based on their place in space, their representation in space. So maybe like this one is 3dyz. So this is the dyz. You can have the dxz, the dxy, and then some different variations thereof. But what this basically does is this shows you what your what they're going to mostly look like. Okay. So now what we have this order of fill. Okay, and I want you to pay very close attention to this. This is something that you're definitely going to want to be aware of on your cheat sheet. So remember that we had n is 1. So go ahead and be taking a look at that table that you filled in. And so when n is equal to 1, all we had was a 1s. Okay, and so you can see that there. Now let's take a look at what some of these are. Okay, so first of all, here's level 1, and it just has a 1s. Now let's take a look at level 2, 2s and 2p. Now take a look at what happens. These start filling out of order. Okay, here you have 3s, 3p, and 3d is over here. And that's because 4s is lower in energy than 3d. So here's our energy level 4s, and you'll start seeing how they sort of pop up out of order, starting there with our 3s. So there's our level 4s. And then here's our level 5. And you can, again, you're going to want to pay real close attention to where these are. Okay. And then here's 6, S, 6P, and 6D. Okay. And I can see here that I missed a 5 in there. And then our last ones, you have 7S here and 7P. Okay, so you can see that they don't follow a normal order. If your question is, does that have to be on order on the test? Yes, it has to be in order in the test, and there's not really any partial credit on this. So if you write it out of order, then you've basically written it out of order. It has to be in the right order for it to be correct. So don't get creative and write it in a different order, because this is the order of fill based on the lower energy levels. So what we have going on here is that right here, this is the lowest energy level. Okay, and over here we have the highest energy. Okay. All right, so the periodic table is broken into S, P, D, and F blocks. So let's go ahead and take a look at that. And what I want you to do on the next slide is I want you to go get your periodic table, and I want you to color code it to some extent. Okay, so you can see here, in fact, I would write all of this on your periodic table. So here we have our S block. Okay, and the S block, you have 1s, 2s, so 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Okay, and these look a little bit different on your periodic table. I'll show you in a minute how this translates into the periodic table that I've given you. Over here, we have the P block. Okay, here we have the P block. Okay, and here you have the 2p, 3p, 4p, 5p, 6p, and 7p. And notice that there is no 1p orbital block. Okay, after that, we have the d orbitals here with the d block, and yours ties these two together. Different periodic tables do this in a different way. I always take the 4 because they put the F block in a different place. So on your periodic table, the D block is your transition metals. Okay, and this is all written into your periodic table I gotta look at mine. And they are great. And the periodic table that I have given you also has these labeled down here at the bottom. You'll see that you have your lanthanides and your actinides, and 4F here, these are your lanthanides. I think sometimes they're also written as lanthanoids. Lanthanoids or lanthanides, same thing. And then your 4F, these are 5F, sorry, these are going to be your actinides or actinoids. They're written as both ways. I think they're written as actinoids on this periodic table because it comes from England, I think. And so they have slightly different things there, but it means the same thing. Okay, so again, write these these into your periodic table so that they will match. And then over here, so you have 4F, 5F, and then make sure that you have your 3Ds, 4D, 5D, and 6D placed correctly. Okay, so actually at this point, what I'm going to do is I'm going to actually flip over very carefully. Let's see, we're going to stop our share real quick in the share screen and come to, oh, sorry, I think it's just, it's just another tab here. There we go. Now we have this one, and actually this is good. I want to show, so we're going to very quickly, I'm going to show you guys how to do this. So right here is your S block. Okay. And what I would write on your periodic table is 1S, 2S, 3S, 4S, 5S, 6S, and 7S on your periodic table. And then what I would do is I would come over here right along this here, and I'm blocking in this group. Okay, just like that. Oops. Sorry, not super neat. Okay, and this is 2P, 3P, 4P, 5P, 6P, and 7P. And you'll notice that the S's and the P's match. Okay, so now the next one that we have right here, you can see from scandium down to lawrencium. This is your transition elements. And see how this is a 4S? So this is going to drop down, and this is going to be 3D, 4D, 5D, and 6D. So there's a drop there. Okay, now hang on just a second. Let's come down to our lanthanides and actinides. Okay, and here you can place that this is our 4F block right here with lanthanum, and that goes right in here. That's 4F. Okay, and then right in here is your 5F, and that goes right here with actinium. Okay, so go ahead again, write those on your periodic table, and we'll be coming back to this. Okay, so here we are on Hund's rule, and Hund's rule and the Aufbau principle. So let's take a look at what these are talking about. First of all, the Aufbau principle requires filling of orbitals starting with the lowest energy and proceeding to the next highest energy level. Okay, so that's where we come in with that 1s, 2s, 2p. Okay, now in every s orbital, remember that we can have 2 electrons. In every p orbital, remember that we can have 6 electrons. In every d orbital, we can have up to 10 electrons. And in every f orbital, we can have up to 14 electrons. And you can look at the periodic table and you can see how that works. So Hund's rule, though, is saying that we can't add things, we can't make them share orbitals until we have to. Okay, so you'll notice in here it says the orbital diagram for carbon. So carbon is number 6 on our periodic table. So here we have electron 1, 2, and 3, 4. But we're going to go 1 and 2 like this for carbon. Okay, so now what I'm going to do is we're going to talk a little bit more about how this works and what an electron configuration is. All right, so notice here that it says to use the periodic table to create orbital diagrams for the following. And what I'm going to do at this point for this slide is I'm actually going to go to a different a whiteboard where I have a little bit more space. All right. So let's go ahead and clear this out. All right. So first of all, we are on slide 14. Okay. And the thing to remember here is that remember that your order of fill is 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S. I want to make sure I don't miss one. I have them memorized, but it'll mess everything up. 5S, 4D, 5P, 6S, 4F, 5D, 6P, 7S, 5F, 6D, and 7P. Okay, and that takes us from our lowest energy level to our highest energy level. And you're going to be able to kind of see where those are. All right, so first of all, let's go ahead and take a look at slide 14. So first of all, we start with magnesium, and magnesium is number 12 on the periodic table, which means that it has 12 electrons. Okay, so what we do is we say, okay, let's kind of work through this. So we have, here's 1s, and that gives us 2 electrons in 1s. And then we have 2s, which gives us 2 electrons there. Now we're up to 4. And now we're up to 2p. We have 2p here. Okay, so there's 4, 5, 6, 7, 8, 9, 10. We're going to 12. So now we have 3s, 11, and 12. Okay, that is an orbital diagram. All right. And our electron configuration for that would be like this. 1s2, showing that there's 2 electrons in 1s, 2s2, oops, I keep wanting to go from 2 to 3. All right, 2p6, because there's 6 electrons there, and 3s2. And this tells us everything that we have in magnesium. Okay, now let's go ahead and take a look at, this is what I want you guys to do, and I will post a picture of this in Brightspace later, probably. No, I might as well just keep going. All right, because you guys can skip over things if you want to. The next thing we have is phosphorus, and that's number 15, which means that we have 15 electrons. And I'll go ahead and start there. We have, so this was 12, so I know I need 3 more. All right. Okay, so here we have 1s, 2s, 2p, 3s. Okay, and after 3s comes 3p. And a really good thing to do is to find this on the periodic table, because that's what we're doing is I'm looking at the periodic table and I'm counting from there. Okay, and I'll show you that in a bit. So we've got now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, and that is our orbital diagram for phosphorus. And now let's go ahead and do our electron configuration. 1s2, 2s2, 2p6, 3s2, and 3p3. Okay. Okay, and then the next one on this section is looking at krypton. And krypton is number 36. Okay. Now I look at where krypton is on the periodic table. You can take a look at number krypton on the periodic table, and you can see that it's at the end of level 4 of row 4. So because it's at the end of row 4, what I'm going to do is I'm going to say, okay, it's at the end of the 4p block. So I can draw this like this, and then I know how far I have to go. So I need my 1s, 2s, 2p, 3s, 3p, 4s, 3d, and remember the d orbitals have 5 in them, okay, 3d, and then 4p, okay, so I have 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p, like so. And then I have to count 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Okay. And then I work my electron configuration, 1s2, 2s2, oops, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. So that's doing orbital diagrams and electron configurations together. Okay. So now let's go ahead and clear everything. And what I'm going to do is I'm going to go back to my PDFs here. And we're going to look at our periodic table. Okay. And the next element here is looking at platinum. Okay. So I'm going to bring this up to here. And right here, you can see where platinum is. You see it right here? Maybe that's not dark enough. Here, there we go. All right, here's my platinum right here, and you can see that it's number 78. Okay, so let's go ahead and work through where we're at. So first of all, we have 1s2 because it's full, and now here we are, we have 2s2, and over here is 2p6. Okay, and then here we have 3s2 and 3p6, and here we have 4s2, and then there we go, 3d10 and 4p6. I'm keeping going until I get down here. All right, now next we've got this row, and that's going to be 5s2 and 4d10 and 5p6. Look where I'm making the check marks up above. Now I'm getting really close to the platinum. Okay, so I come here. Now I'm finally in that row, and that's 6s2. And then we're right here, those lanthanides. Okay, and that means 4f14. Okay, and then finally, we're right here in our 5D, and there's 1, 2, 3, 4, 5, 6, 7, 8. And so there's my electron configuration for platinum. Okay, all right. Now the next one is, let's see, samarium. All right, so we got to find samarium, and samarium is right here. It's number 62, and here we are in the lanthanides. So now we're going to do the same thing again. All right, so first of all, we have 1s2. Okay, and again, I'm making check marks as I write them down. 2s2, and then over here, 2p6. Okay, and then here we have 3s2 and 3p6. And here, 4s2, 3d10, and 4p6. All right, and next row, 5s2, 4d10, and 5p6. Okay, and now finally we're in the row where we're going to find 62 because it's right in here. Okay, and so we have 6s2, and then we drop down to our 4f's here, and we've got 1, 2, 3, 4, 5, 6, 4f6. And that is our electron configuration for samarium. Okay. All right, and one more. Oh my goodness. So now what we're doing is we're looking for bismuth. That's the last one, and that's number 83 right here. Okay, and we'll go ahead and start it again. So we have 1s2, and we have 2s2 and 2p6, and we have 3s2 and 3p6, and we have 4s2 and 3d10 and 4p6 and 5s2, 4d10, 5p6. And now we're finally down in our row, and that gives us a 6s2, and then a 4f down here, 4f14, and a 5d10. And finally, we're up to our 6p's, 1, 2, and 3. And we have 6p3 for up here. All right, so that's how you do those. You should be able to do quite a few of them. We're getting close to done. Okay, and we are here. Okay. All right, so let's go ahead and talk about some periodic trends in atomic properties. There's atomic size, ionization energy, and electron affinity. And I actually don't talk about electron affinity very much, mainly because there are a lot of exceptions to the rule. And so I always find it better to just ignore electron affinity altogether because it's easier to talk about it in terms of electronegativity in a different chapter. Okay, so let's start by looking at atomic size. So the shell where we find the valence electrons affects our atomic size. So as the size of the valence orbitals increases with our energy level, so size must increase from top to bottom of a group. Okay, so I'm going to just kind of draw over here kind of a little mini periodic table. Okay, so as we go down the periodic table, we get bigger. Okay, now as we move across the periodic table like this, what's happening is that we're adding these protons one after the other, and those protons are very positive, and they're going to pull harder on our electrons, which means that we're actually going to get smaller as we go across the periodic table like this. So you can kind of draw an overall trend going in this direction, and these are your smallest, and these are your largest. And that's kind of that overall trend that we have there. Okay, this is just showing you a little bit of an idea about what's going on. So here you have in row 1, you have your greens right here. Okay, this is row 1, or this is N is equal to 1. Okay. And then our next one, we have kind of a purpley color right here. And but this is N equal to 2. Okay. And the next one that we have right here is N is equal to 3. And you can see what the trend ends up looking like. And here we have N is equal to 4. And you can look at your periodic table and you can, and these are the elements that go with that. All right. Right here, we have row 5, or N is equal to 5, with everything in there. Okay. All right. So row 5 and finally row 6. Okay. Now it says use the periodic table to rank these elements. All right. So what I'm going to do is we're going to come over to the periodic table. And we're going to find those elements. Okay, so those elements, you're hopefully looking at your notes template. First of all, the elements that we're going to link are, we have rubidium right here. And we have potassium is one of those. Okay, and we have iron right here. And selenium. And we have sulfur. Okay, so remember that we said that up here at the top were our smallest elements. And I have things in the way over here. I don't know if you'll be able to see this, but we have our smallest elements up here and our largest elements here. Okay, so if we are going to rank these in terms of increasing size, so remember that increasing size means getting bigger. So, yeah. Okay. So now we can just sort of work that. So based on this trend, that means that sulfur has to be our smallest, and then selenium, and then iron, and then potassium, and then rubidium. And you can follow this on your periodic table. Okay. Okay. So now we're talking about ionization energy, and ionization energy is the energy required to remove an electron from a gaseous atom. But all you really need to remember there is it's the energy required to remove an electron. Okay, so again, let me go ahead and draw my little periodic table here so that you can kind of see what's going on. The more strongly held an electron is, the higher the energy level. Okay, so that means that ionization energy increases when we go from left to right. So here, ionization energy gets bigger. Okay, but as we go down the periodic table, the electrons are moving farther away from the nucleus, and so they're easier to remove. So here, our ionization energy gets smaller as we move down the periodic table. So that means that on the periodic table, we could draw this line like this, and these are the highest ionization energies. And these are our lowest ionization energies. And remember, a high ionization energy means that it's hard to remove an electron. And a low ionization energy means that it's easy to remove an electron. Okay. So this is a really interesting little graph, though, that shows where it doesn't follow. So remember on the atomic size graph, everything was nice, perfect little little things, but you'll notice that this one isn't. Okay, so let's take a look at what that means. Notice that we go up from hydrogen to helium, great. But then we start on our next row. So this is row 2 right here. And we have these stair steps from beryllium to boron, and then from nitrogen to oxygen. And then you'll notice that we kind of do that again right here. This is in row 3. Okay, and going from magnesium to aluminum, we go down, and then from phosphorus to sulfur. So we go up and then back down. And I actually have this on your I have a similar one on your chart. Okay, on your notes template, sorry. Okay, so let's take a look at what that means. And okay, so from beryllium to boron, hopefully you're looking at your notes template right now. There's a slight decrease in your ionization energy because beryllium has filled its 2s orbital, but boron places a single electron in its 2p orbital. And you can see that. You should look at the periodic table right now and find where those are. Okay, the 2p orbital is higher than the energy in the 2s orbital, and that means that it is easier to remove that electron because it's kind of hanging out there all by itself. I'll show you in a minute on the periodic table. And then from nitrogen to oxygen, we'll see that there's also a slight decrease, and that's because nitrogen has a half-filled p shell. Remember that nitrogen looks like this, 1, 2, and 3. Okay, but oxygen looks like this, 1, 2, 3, and 4, because it's because of where it is. It has 4 valence electrons there. Now, this electron right here is easier to remove because it's basically sharing a room, and the other electron is like, get out. Okay, and that's what lowers its ionization energy. All right, so now our last slide here is telling us that we are going to be ranking our elements. Okay, so hopefully write these down if you don't have a notes template handy, and let's take a look now. Okay, so first of all, the first things that we're going to rank are going to be bromine, and I'm just going to circle them again because it's so easy to see that there. We've got bromine and we have fluorine, okay, and we have gallium, which is right here, okay, and we have potassium over here, and we have selenium right here. Okay, so what we're going to find is in order to place increasing ionization energy here, okay, so increasing IE, so what we want to do is we want to have our low IE to high ionization energy. Okay, and the easiest way to do that is to just start here, because remember it goes like this, is to start here at potassium, and we're just going to draw a line like this and then straight up, and that's going to define, I don't even need to look them up, so I know that it's going to be potassium and then gallium and then selenium and then bromine and last fluorine with our highest ionization energy, and you can just see that based on this trend completely. Okay, now the next one is a little bit harder. You'll notice that it lists silicon, okay, and it lists carbon and nitrogen and phosphorus. Now, these are all close together in this little block. So we know that the ionization energy is going to go up as we go across like that. But the question is carbon and phosphorus. Which one is it going? Which one is going to come first? Okay, so when they're really close together like that and you're doing your homework, or but take a look in your textbook. For anybody, that's our Chemistry for Engineers by Brown and Holme textbook, and it's table 6.4 lists your first 4 ionization energy for some of your top ones there. And you can actually see, if you look in that then from a low ionization energy to a high ionization energy, the order then is a little bit easier to predict, whether it's silicon, phosphorus, carbon, nitrogen, or silicon, carbon, phosphorus, nitrogen. But we can see, if we look at those, that it's going to be silicon and then phosphorus and then carbon and nitrogen. Okay. And that is it. That's the end of our chapter 6. Your homework will be posted in Brightspace. Let me know if you have any questions during office hours or during our next class. Thank you.